Dear students, again in this series of lectures on the course Analog Electronics, I am again here with the same topic and with another lecture on the topic of bipolar junction transistors. So before I start the lecture, let me give you the outline of the lecture. So here, first of all, I'll be discussing about your transistors in the active region. That is, how do we bring the BJT or the transistors in active region operation. Then I'll be discussing about the various current components in a transistor or a BJT. What are the various current components, on what factors those currents and the current components are dependent. So we'll be discussing about this, and then finally we'll be discussing about the base width modulation or the early effect, which is there in the BJTs or the transistors. So coming to the active region operation of the BJT, this active region operation of BJT is one of the most important amongst the three modes of operation of BJT. So it's worth discussing about this operation mode. So mainly we can describe about this operation of BJT using this figure, and for this purpose we'll be considering a PNP transistor, and in order to bring the PNP transistor in active region of operation, mainly you know that there are two junctions in a BJT or a transistor. The first one is your emitter junction, and this junction is between the emitter and the base, and the second is your collector junction, which is the junction between the base region and the collector region. So in order to bring the PNP transistor or any transistor in the active region or active mode of operation, what we do, we bias these two junctions in such a way that the emitter junction is forward biased, this emitter junction is forward biased, and the collector junction JC is in the reverse bias conditions. So in order to, it can be explained here by this figure A. Here this your first biasing voltage which is connected across the emitter and the base junction, that is VEB. It is connected in such a way that your junction JE is in forward biased condition. How this JE is in forward biased condition? You know that the emitter side is a p-type semiconductor and the base is a n-type semiconductor. So we have connected this biasing voltage in such a way that the positive end of the battery, that is this positive end, it is connected to the emitter side, which is a p-type semiconductor, and this n or you can say the negative end of the battery or the negative terminal of the battery, it is connected to the n-type base. So in this way we have this JE as in forward biased condition. Similarly, what we have done, in order to make this junction JC, that is the junction between the base region and the collector region, in reverse bias, what we have done, we have connected a voltage VCB. Here it is VCB actually. Now this voltage VCB is connected in such a way that the junction JC is in reverse bias condition. So here you can see this positive terminal of the battery, it is connected to the n-type base, and the negative side, it is connected to the p-type collector. So in this way your junction JC becomes, or it comes in the reverse bias conditions. Now what will happen with the with this biasing or with the connection of these biasing voltages, what will happen to the transistor or what will happen to the barrier potentials? Basically we can just visualize the change in the barrier potentials through this figure B. Here these dotted lines, they represented the barrier potentials across the junctions JE and JC when there were no biasing voltage connected to the BJT. But once we connect the biasing voltages, the change in the barrier potentials, they are represented by these solid lines. So here what we observe from this figure, you can see that as earlier when no biasing voltage was applied, the barrier potential was V0 in this case, and similarly it was also V0 in the case of JC. Because we have taken the construction as symmetrical, so the barrier potential was equal at your JE and as well as at JC. Now if you connect the biasing voltage, what happens? The change in the barrier potential across JE is in such a way that the barrier potential here, it is decreased by an amount of absolute value of VEB, which is the biasing voltage. Similarly, what happens at the JC or the junction at the collector junction, the biasing voltage, it is added up and the potential barrier, it rises by an amount that is VCB. So this can be visualized by the figure, by figure B here. So again, what we have done, we have taken the space charge region as negligibly small, and they are not shown in this figure. We have considered this space charge regions at or near your JE and JC or the emitter and the collector junctions to be negligibly small, and hence these space charge regions, they are not shown. Now as I have already told that the forward biasing of JE, it lowers the barrier potential V0 by an amount equal to the magnitude of the applied emitter base voltage, which is VEB or absolute value of VEB. Similarly, the reverse biasing of JC or the collector junction, it increases the barrier potential, as we have already discussed, by an amount equal to the magnitude of the applied collector base voltage, that is the absolute value of VCB. Now what happens then? This lowering of the emitter base potential barrier, it permits the injection of the majority carrier holes of the emitter region towards the base region, and the majority carrier electrons of the base region, they are injected into the emitter region. So what happens basically, you know that the majority carriers are holes on the P side, which is the emitter region, and the majority carriers on the N side base region, they are electrons. So in case the barrier potential at JE, it gets reduced, what happens? Your the majority carrier holes, they are injected from the emitter region towards the base region, and the majority carriers which are electrons on the base region, they are injected into the emitter region. So this is a kind of transfer of charges from one side to the other side across the junction, that is JE. Now in this case, what will happen? With the transfer of the charges, the minority carrier electrons in the emitter, okay, so the electrons are minority carriers, minority charge carriers on the P side of the or you can say on the P type semiconductor side, emitter side. So this basically the minority carrier electrons on the emitter side, which is represented by NP, it rises exponentially from the thermal equilibrium concentration. Suppose if you take the initial value or the value of your minority charge carriers on the P side during the thermal equilibrium to be NP0, now it increases to another value, that is NP0 in brackets at this emitter junction. Fine. So now this rise in the minority charge carriers, it is given by this formula, that is NP0 in brackets is equal to NP0. What is this value? This value is the concentration of electrons in the P region at during the thermal equilibrium. So this value, it changes exponentially this is your applied, VEB is your applied biasing voltage across JE, and VT is the thermal voltage. So this is the formula which governs the change in the concentration of the minority charge carriers in the emitter side. Similarly, what basically happens to the minority carrier holes in the base. So suppose the minority carrier holes in the base region, it is represented by Pn. Their value also rises exponentially from the thermal equilibrium concentration, which is given by this Pn0 to Pn0 in brackets. So suppose this is given by Pn0 in brackets, it is equal to Pn0 e raised to power of VEB upon VT. So this formula again, it governs the minority carrier holes, or it governs the representation of the minority carrier holes in the base. Okay, so both these equations, this equation and this equation, it shows that there is exponential rise in the value of the minority charge carriers in both the regions. So you are aware that because of the doping at thermal equilibrium, the concentration of holes, it is larger than the concentration of electrons. That is, Pn0 is very high than Np0. So because of this, why this is there? Because your emitter side is heavily doped and the base side is lightly doped. So because of this, we can say that this Pn0, or the rise in the minority carrier concentration in the holes, it is greater than the rise in the minority carrier concentration of electrons. So these two values we can visualize in that way just because of this relationship. Then similarly, what happens at the collector junction? Earlier we were talking about the previous two equations. We were talking about the concentration of charges near the emitter junction. Now we are talking about the concentration of charges, or you can say the minority carriers at your JC, that is collector junction. So similarly, here again, the minority carrier holes, that is Pn in the base region and electrons Np in the collector near the collector junction JC. Suppose we are taking the concentration at a distance x equals to W from the emitter junction. So these two formula, again similar to the previous two formulas, they govern the values of minority carrier concentration near the collector junction region. So this is given by P and W equals to Np0 e raised to power of VCB upon Vt. So here since we are talking about the collector junction, the region near the collector junction, so this VEB, which was earlier in the formula, it has been replaced by VCB. And similarly here also for the concentration of electrons, again this is given by Np0 e raised to power of VCB upon Vt. So we know that this VCB is negative. VCB is a negative because the junction JC is taken in reverse bias conditions, and the absolute value of VCB is very high as compared to the thermal equilibrium voltage. So what will happen? Because of this relationship, this P and W, that is the hole concentration at a distance W from junction JE near to the junction JC, and the concentration of electrons will be equal to, or they will simply reach to this value 0. Now this variation of the minority carriers, they are depicted by solid lines in the previous figure as I had shown you in this figure. These solid lines, they depict the variation of the minority carrier concentration, okay, in these regions. This is your emitter region, this is your base region, and this is your collector region. So the excess holes, what happens? The excess holes mainly are basically the excess Halls from the base. They diffuse from the emitter base junction JE to the collector base junction JC across the base where the electric field intensity E is 0. Okay, because of biasing voltages, what happens, the Halls which come from the emitter region, some of the Halls they get intermixed with the electrons in the base region, and mainly the excess Halls, okay, the excess Halls in the base region, they diffuse from the emitter base junction JE to the collector base junction JC across the base region where the applied electric field intensity is 0. So now what happens, the junction, since the junction JC is in, that junction JC is in reverse biased, hence the electric field intensity E at the junction JC will be positive and large. So what will happen, the Halls which are coming from the emitter side will be accelerated across this junction JC, or in other words, what we can say, the Halls which reach the junction JC, they fall down the potential barrier and are therefore collected by the collector. Okay, so what does it mean? It means that the Halls which are the majority carrier, they reach the base region, and similarly they gets diffused from the base region to the collector through the junction JC. So this is actually what happens, and what this thing has been explained through these sentences. Now coming to the next topic, that is the various current components in a transistor. In this section we will be discussing about the various components of current in a BJT during its operation in the active region. So again we are considering the active region operation of the BJT. In the active region, you know that JE is forward biased and JC is reverse biased. So what happens, the majority carrier Halls from the emitter region, this you are already aware and we have discussed, these majority carrier Halls from the emitter region, they are injected into the base region, and the majority carrier electrons of the base region, they move into the emitter region. So what happens then, the emitter current, mainly the emitter current, that is IE, it is then composed of two components. The first component is, suppose, IPE, and this IPE is basically the Hall current constituted by the movement of Halls from the emitter side to the base side. Fine. And the second component is INE. Okay. This subscript E represents the emitter current, and this N represents the current due to electrons, and P represents here current due to Halls. Okay. Now this INE is the electron current due to the movement of electrons from the base region to the emitter region. Now mainly this forward biasing of JE, it increases the population of Halls in the base region, which will finally produce the collector current. So to have the collector current, this collector current IC, suppose, this collector current is to be made proportional to the emitter current. And the emitter current then should only be constituted by the Hall current, that is IPE. Okay. So in order to make this collector current proportional to the the collector current proportional to the emitter current IE, the emitter current, it should only be composed of the Hall currents, or the current due to the electrons should be negligible in this case. So the electron current, which is INE, it should be negligibly small. And how this is made possible? This is made possible when the emitter is heavily doped and the base is very lightly doped, which is normally done in the case of transistors. So why it is there? This is just to make the emitter current, or you can say make the collector current proportional to the emitter current, or just to make the emitter current simply exclusively made of the Hall current. Okay. So this is why this can be made possible only if you change or you vary the duping from the emitter side to the base side. So it is assumed that the injection of electrons into the base region is a low level injection. What does it mean? Because of this low level injection, the minority carrier current, that is IPE, is a Hall diffusion current into the base, and its value is proportional to the concentration gradient of Halls at JE. And this value IPE, that is the Hall current, it is given by this formula, that is minus Q dPAX, derivative of Pn upon dx, where dP is the diffusion constant for Halls, A is the area of cross section, and Q is the charge on an electron. Similarly, the electron diffusion current is proportional to the concentration gradient of electrons, and it is given by this formula, that is INE equals to minus Q d raised to dN into A into derivative of Np upon dx, where Dn is again the diffusion constant of electrons. So the total emitter current, this IE, it is given by two components, that is IPE plus INE. So here the direction of these currents, they are shown in this figure. It can be observed, the various currents can be observed here, and suppose these currents, or the direction of these currents, are shown in this figure we are referring to, which are all positive, flowing from the emitter to the base, as these are the conventional currents. So the currents flowing from emitter to base, they are considered to be positive, and if any current is flowing just opposite in this direction, it is considered to be negative. The holes on crossing the emitter junction diffuse through the base region, and in this process some of the holes, mainly they combine with the majority carrier electrons in the base region. This we have already discussed. So what happens, basically because of this, the number of holes reaching the collector junction will be less than the number of holes emitted at the emitter base junction. So in order to reduce the possibility of this recombination in the base region, the width of the base region is made extremely small. Okay. So if you say that IPC1 is the Hall current at the collector, this IPC1, it is the Hall current at the collector junction JC, which is due to the holes reaching this junction through the base region. Then the current IPE minus IC1, this current which is shown here, it is the recombination current which leaves the base. This current, it actually leaves the base, it is shown here in this figure. So the electron, it enters the base region from the external circuit through the base lead to supply those charges which have been lost by recombination with the holes injected into the base across JE. So what happens? So whatever is the recombination of charges here, it is given again into this base region externally. Fine. So coming on to the next point. So for the time being assume that JE is open circuited, that is the emitter junction is open circuited, so that the currents IE and IPC1 are equal to 0 and JC is reversed biased. Okay, this JC or the collector junction is under reverse biased condition. So under this condition, what happens? The collector current IC, it will be equal to the simply reverse saturation current ICO of the base collector junction, which simply works as a reverse bias diode. So you know that we are now considering that JE is open circuited, and we have simply connected the biasing voltage across the collector junction JC, which is in reversed bias. So it simply behaves as a PN junction diode, and the collector current, it will be now not dependent on your emitter current, but instead it will be simply dependent on the reverse saturation current, or ICO. Okay. So this reverse saturation current ICO will be the sum of two currents, that is ICNO and ICPO. This ICNO is the current due to the movement of the minority charge carrier electrons across the junction JC from the collector, that is P type, to the base N type, while this your ICPO is the current due to the movement of the minority charge carrier holes across the junction JC from the base N type to the collector P type. So this collector current, it can be represented by this formula, that is minus ICO equals to INCO plus IPCO. Now this negative sign here in this formula, it is chosen arbitrarily so that your IC and ICO will have the same sign, because the reverse saturation current and the collector current, they will have the same sign. Now we once again return back to the original situation where your JE, that is JE or the emitter junction, is in forward bias condition, and under that condition your current IE, that is your emitter current, it will be not equal to 0. So now this collector current IC will be equal to ICO minus of IPC, or simply if you replace this IPC by this term alpha IE, fine, it can be, this equation will change to this equation, that is IC equals to ICO minus alpha IE. So where alpha is defined as the fraction of the total emitter current IE that represents the holes reaching the collector after traveling from the emitter through the base. Now since ICO is small enough, so this alpha, it can be taken as the ratio of the collector current IC to the emitter current. Suppose if you take this value, it is equal to 0 because it is very small. So this your alpha is simply the ratio of, what will be this alpha? It will be simply the ratio of IC upon IE. Fine. So now if you want to find out a generalized equation, a generalized transistor equation, as the equation above, basically it represents the collector current IC when the transistor is in the active region, and also this current is independent of the collector voltage. So in order to obtain such generalized equation for the collector current, which should also be valid not only when the collector junction is reversed biased, but also valid for any voltage across the JC, we replace the term ICO in the above equation by IC, which is the diode current. Now you know that the diode current, it is given by this formula, that is I equals to Is e raised to V upon Vt minus 1. So what we do here in this equation, we replace Is by minus Ic0 and V by Vcb in this equation. So now if you replace this, how this equation will change? This equation will be represented as this equation here. So it will be Ic equals to minus alpha IE plus Ic0 or ICO 1 minus e raised to Vcb upon Vt. So now if VCB is negative and it is larger than VT, this above equation, it will be simply reduced to IC will be equal to minus alpha IE plus IC0. Okay. So coming on to the next point, that is your base width modulation. Base width modulation. Now for understanding this concept of base width modulation, we again consider a PNP transistor which is operating in active region, whose emitter base junction is biased in forward direction and the collector base junction is again biased in the reverse direction. The reverse biasing of the collector base junction in the transistor, it acts as a sink of the minority charge carriers injected into the base region from the emitter region. Basically here why we have used this term minority, because the majority charge carriers which are injected from the emitter side to the base region, they become minority charge carriers. So here we have used this term instead of majority charge carriers, we have used the term minority charge carrier. Now it is well known that the width of the depletion region or the space charge region near the junction is large when the junction is in reverse bias, and this width, it increases with the increase in the reverse bias. Okay, so you know that if you increase the value of the reverse bias voltage, then the width of the junction under reverse bias, it increases. So what happens? So the width of the depletion region W, it is large at the collector junction JC. Suppose if you take the width of the depletion region to be W, then it is large at the collector junction JC as compared to the value at JE, because this JC is in reverse bias condition and JE is in forward bias condition. Now since the emitter base junction is in forward bias, so the width of the depletion region is negligibly small at this emitter junction, that is JE. Now since the doping of the base is ordinarily or substantially smaller than that into the collector, so what happens? The penetration of the transition region in the base near the collector junction JC, it will be larger than into the collector. Okay, so hence the whole of the depletion region may be assumed to be in the base region here, as it is shown in this figure. Fine, in this figure A. Now if you take WB as here, WB here, that is in this figure, if you take here in this figure, sorry, here, like this WB in this figure. So if this WB is the metallurgical, metallurgical base, let me take a pointer option. So if this WB is the metallurgical base width and W is the width of the depletion layer, now as the collector voltage, that is VCB, it is increased, the space charge layer takes up more of the metallurgical base width, that is WB, and as a result what happens, this effective base width, which is WB dash, it is decreased and it is given by this formula, that is WB dash equals to WB minus W. So now this effect is given by, this effect was given by J.M. Early, and it is known as base narrowing or base modulation or Early effect. Okay, the modulation of this effective base, that is WB, it also with the increase in the collector voltage has basically three consequences. The first is that the possibility of the recombination within the base is reduced, thereby increasing the collector current. Hence what happens, this alpha, this increases with the increase in VCB. Now the second consequence is the concentration gradient of the minority charge carriers increased within the base region with the increase of the VCB, and consequently this Hall density, that is JE, Hall current density JE, and then IE, it increases. Okay, and finally this consequence, or the last consequence, it can be given as, for this extremely large reverse bias at the collector base junction, the width of the depletion region, it becomes too large. Consequently, the effective base width, it reduces to 0, causing the voltage breakdown in the transistor. Okay, so now this breakdown is basically called punch through or reach through. So this was all about the 3 topics in this lecture. Once again, I request you to come up with the doubts in the group if you have. And this was all about this lecture. Thank you very much.